So now let's look at compound interest in a different light. As we saw, the more times that you compound it, the more money you're going to get in that account, the more interest you're going to get. Now, the problem is, of course, is that you reach a limit. You can't increase forever. So if we wanted to reach that limit every single time, we're not going to use this compound interest formula. And we have a new kind of compound interest, which is called continuously compounded, which just means that it's always being computed. It's not daily, it's not hourly, it's just always happening. Now, in a real situation, a bank is not like sitting there like every second of the day trying to compute this. It's just at the end of the quarter, at the end of the month or whatever, when you get your statement, they would have used that formula, they computed it, and make sure they put that money in your account. Okay, so basically what you're about to see in this formula is, look right here in the parentheses with the compound interest formula, the 1 plus r over n raised to the n. That almost looks like the limit definition for E, and that's exactly what this turns into. So here is the formula for continuously compound interest. It's a very, very useful formula. As a matter of fact, we're going to use it more than just with compound interest. We're going to use it as an exponential growth and decay model in just a little bit. Okay, so it's the amount that your account's worth is equal to P is principal, times E to the R, that's your percentage rate, so maybe it's earning 3% per year or something like that, times time, whatever your time period, 3 years, 5 years, whatever. So usually we call this the PERT model, because you can see very clearly it just spells PERT. It's easy to remember and it's pretty easy to use too. So let's use it right here. It's the same numbers that we examined way at the beginning of this lesson, or maybe it was the middle of it. So still $5,500 in your account, and your interest rate is 3.6%, and we're putting it in there for 10 years, and how much money are we going to have? So we're using this PERT equation, so A is equal to that 5,500, that's the P, E to the R power, write that as a decimal, 0.036, times my time, which is 10. Calculator. Ruther. Okay, so type in the original principal, $5,500, E, so I want to use this one over here on the left side, where's the E to the X, and inside the caret. Now if yours doesn't put the exponent up there, if you have the old operating system, put these in parentheses. It may open the parentheses for you, if I'm not mistaken. So 0.036 times 10. Okay, and so here we go. We'll have to round that to the nearest cent. So $7,883.31, and that's the most amount that bank account could possibly get it at that interest rate. Remember, that's the limit that bank account could possibly get in it when it's continuously compounded interest. Okay, so what about if I just wanted to know how much interest I got? So what we were seeing before is like it takes the interest and it puts it back into the account, and it gives you the amount of the account after that's all done. So I want to know, how much interest did I get? Just the interest part. Okay, so that's a pretty easy thing to do. If, well, I'll write it as interest. Interest. If the amount in the account is the PERT model, so P times E to the RT, that gives you everything in the account. In order to get just the interest, I just subtract out the original amount, so minus P. Well, then you got it, right? So here's my account with all the stuff in it, with all the interest and the principal. Just take the principal away. What you're left with is just the interest.
And this is my dance dance. Hey! Ding dang 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 dang. Da 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 da. Dang 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 dang. Ding ding ding. Ding ding ding. Ding ding ding. Ding ding ding. dun, dun, dun. 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 What's that for? Dun, 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 dun. Dun, dun, dun.
Okay, so in many real life situations, it's kind of unrealistic to say that like the population of maybe like an ant colony doubles every 4 or 5 days. Does that mean like I wait 4 or 5 days, let's just say it's 5 days, and then bam, it doubles, and then I wait another 5 days, bam, it doubles? No, that's not really what's happening. What's happening is that it's continuing to grow, and then by the time you reach the 5 days, it would have been twice as big. And so the model that does this most accurately is this PERT model. And so we use it as continuously growing our exponential growth and decay. So notice it's the same exact equation, just take the a out and put a y in its place, whatever, it's the PERT model. And we're going to use that equation. If the r value is greater than 0, it's exponential growth, and if it's less than 0, it's exponential decay. So all I'm going to do here is one extra problem, I think, and that's re-examining the population of Denton question. And that is, like if you're going to do some sort of population projection, you're probably going to use the natural base, the E, instead of like what we used before. Okay, so this is very, very easy to use. I'm going to write it up here so that I can see it with a calculator whenever I pull this up. Y is equal to P, the principal, and that principal is the amount that I start with, 119,454 times e to the r. My r rate is right there, written as a decimal, 0.0301 to the t. Let's see, this was 2020 from 2008. I think that was 12 years. So you'll see how easy this is to use this formula. So clear this out, 119. So the hardest part is just accurately typing things in. 454E. Where's that at? Oh yeah, and finding stuff on the calculator. 0.0301 times 12. So here's our prediction for the population. And if you recall what we got the first time, I think this is about 1,000 more people. Where did all those guys come from? Or girls, whatever. So there you go. That's what this model predicts for 2020 in Denton, Texas. Okay, so that wraps up our lesson on exponential functions. It was a pretty long journey. We did things like, well, we defined what exponential growth and decay was, what an exponential function is, where your exponent is the variable this time instead of like the base or whatever. And we were able to model some real-life situations with exponential functions like population and money and depreciation, and calculating some compound interest. And we tied all those things together essentially with this new number that we got called E, which is the base of the natural exponential function. You're going to see it's going to be the base of the natural logarithm in the next lesson too. So there's a little cartoon for you, haha. And here's your assignment. Rowan, these lessons are getting exponentially longer? You mean exponentially better, don't you? All right, well, I'll see you in class.